Distinguished guests, ladies and gentlemen, welcome back to our Science Symposium. I hope you enjoyed the lunch. And their upcoming session is Mathematics Sessions, Insights into Mathematics. For this session, I would like to introduce with you Professor He Shuwa as this session's convener. He is Chair Professor and the new Cornerstone Investigator, Department of Mathematics, the University of Hong Kong. Member, Program Committee of the Future Science Prize Week 2024. Let's put your hands together to welcome Professor He.
Good afternoon, distinguished guests, ladies and gentlemen. So glad to see you in Hong Kong. It's my pleasure to be the convener today. First, I would like to extend a welcome to all of you and my gratitude to all speakers accepting our invitation. The topics of today's section is Insights into Mathematics. I hope that today's speech and the panel discussions will offer you profound understanding and stimulate sort of a conversation about mathematics. First, allow me to introduce our first speaker, Professor Jian Ding from Peking University. Professor Ding has made significant contributions to the field of probability theory, emphasizing its interaction with statistical physics, theoretic computer science, and statistical learning theory. He is the laureate of the 2023 Nobel Prize in Probability. He's going to deliver his speech titled A Glimpse at Statistical Physics from Percolation. Through examples, he will describe various percolation models in statistical physics, with emphasis on phase transition, critical phenomenon, as well as disorder efforts. Let's welcome.
Thanks for coming, and thanks for the invitation and a very nice introduction. It is a great pleasure and honor to speak on this occasion. Today I'm going to tell you something about statistical physics from the perspective of percolation. So what is statistical physics? Well, to put it in a simple way, basically the goal is to understand complex, macroscopic, and deterministic laws in physics via simple, microscopic, and stochastic mechanism. This subject, you see joint efforts from physicists and mathematicians. Usually, the physicists would provide very insightful predictions via non-rigorous derivations and numerical studies. So what do we mathematicians do? Most of the times, we rigorize and clarify physicists' predictions so that we can give them a consolidated ground for further predictions. And occasionally, we can actually correct what physicists predicted. And in some occasions, mathematicians did discover phenomenon that has been elusive to physicists. This is a subject in its prime time. There are many interesting problems, and many of them have seen substantial progresses recently, which lead to major prizes in both mathematics and physics. So I'm only going to choose one facet of statistical physics to talk about today. It's an important facet, and the perspective is from percolation models. So what is percolation? The history of percolation is rooted from the coal industry. People are interested in the permeability of porous medium, i.e., whether water can pass through some porous material. And experiments in 40s discovered that the permeability of this porous material it depends on the temperature and also the type of liquid you are considering. In fact, percolation models are very commonly seen in the nature from the natural sinking of water into the soil, or whether fire forest is controllable or not, or the clustering structure of cells in the tissue. In fact, in everyday life, whenever you boil a cup of coffee, you are doing a small experiment of percolation. Now let's move to the mathematical side of percolation models. Canonically, when we talk about percolation, it refers to the Bernoulli percolation model introduced in the 50s. It is perhaps the simplest model. It just says, say, on a lattice, every edge or every vertex is chosen to be open or closed with the same probability independently. So here, if an edge is open, it means water can pass through that edge. Then you can see, mathematically, the permeability of water corresponds to the macroscopic open clustering structures in the percolation model. Here are some illustrations for either bond or site percolation models on a few different lattices. Two of them are in 2 dimensions, one of them is in 3D. As I said, we care about whether water can pass through the material or not, and this corresponds to whether we have an infinite open cluster in the percolation model or not. And this is, as a result, this is the major goal in the study of percolation. Let's look at the Bernoulli percolation on Z2, because Z1 is the simplest, but it's kind of trivial. Z2 is the first interesting and non-trivial example, and actually has quite rich phenomenon. So the fundamental question is whether there exists an infinite or macroscopic open cluster, or we can just ask whether there is a positive probability that the origin can be connected to infinite via an open path. An open path is a path so that every edges along the path are open. Then we can define this critical threshold. Clearly, this should depend on P, right? If you increase P, you should increase your probability of finding an open path. So we can define the critical threshold, PC, to be the infimum of the P so that this event happens with positive probability. Note that this event cannot happen with probability 1 because we're looking at the origin. There's always some probability that the origin is just broken already or the neighboring edges are broken. Now we can wonder, what can we say about PC? We know it should be between 0 and 1, but is it strictly between 0 and 1? A moment of thinking leads to, okay, there should be some non-trivial lower bound. For instance, here's what we can do. Suppose we want an open path from the origin to the infinite. That means for every n, we should be able to find a self-avoiding open path of length n, starting from the origin. And for each such path, the probability of being open is just the p to the power of n, because we want all edges being open, and these openness are independent of each other. Then naturally you would wonder, how many paths of this kind you have in total, right? There should be some bound you can get easily, like 4 to the n is the simplest bound, because the degree is 4 for each vertex in Z2. But you can do a little bit better and get a 3 to the power of n, because a self-avoiding path naturally cannot be backtracking. That only gives you 3 possibilities for where you go next, for the next step. So you get 3 to the power of n is an upper bound. Then you put this probability calculation and the enumeration together. You get that, okay, PC has to be greater or equal to 1/3, because otherwise a simple union bound or simple counting argument like this tells you that there's no way you can find an infinite open path. Now you would wonder, can we do better? Is 1/3 at the sharp threshold or not? There are 2 types of questions here, right? First, when we count the number of self-avoiding paths, is 3 to the power of n good enough? Is that sharp? 2, provided with a sharp estimate on the enumeration of self-avoiding path, can we get the sharp critical threshold via this method? Well, the answers to both questions are negative. Our bound on the enumeration of self-avoiding path is certainly not sharp, because we only consider that in one step you don't want to go back, right? But you certainly have to also avoid, say, small cycles. And every 4 steps you want to avoid a small cycle that should also further limit the number of choices for your path. this means that we didn't get a sharp answer for the enumeration of self-avoiding path. In fact, self-avoiding path itself is a very important and challenging model in statistical physics. It was proposed to model the polymers, I think by a Nobel Prize winner in chemistry. Its enumeration is also a very difficult problem, and only in a lattice, in two-dimensional lattice, like not Z2, but honeycomb lattice, this was solved by Dominic Kopan and Smirnov, both are Fields medalists. So that's the first comment. The second comment is, suppose somehow you can actually compute the exact enumeration for the number of self-avoiding paths. Can you use this method to get the exact critical threshold? The answer is also no. So basically, this type of counting method is a little too simple to tell you something about near-critical behavior. In all these statistical physics models in lower dimensions, if you want to understand what happens near criticality, you would have to find some more sophisticated methods than just the counting method I described here. Okay. And in a similar manner, you can also get an upper bound on PC. This basically by some sort of duality consideration. Just imagine now you want to grow your open set. And you want to say, if you want to confine this open set into a finite zone, at some point, all the boundary edges in your open set have to be closed, right? So you have to be able to find some sort of closed contour to surround your origin. If you just do some duality consideration, this would say, okay, you should be able to find some closed self-avoiding open loop in the dual model, and a very similar calculation to what we did above give you that if P is if P is larger than 2/3, then this would fail. So this says that PC has to be between 1/3 and 2/3. Now, a natural wonder is, can we actually calculate the value of PC via some other methods, right? This is actually a quite difficult problem, and we can only calculate it in very special cases, basically in 2 dimensions. And I can tell you that on Z2, we know the answer. By we, I mean the community, not I. The answer is PC equal to 1/2. Here is a very rough heuristic, and we can see what is the flavor here. The first ingredient is some rotation invariance. This is not very hard. This basically says if you have a square box, the probability that you find the left-right crossing and the probability you find a top-down crossing, those are the same because the model is invariant if you rotate it by 90 degrees. The more sophisticated ingredient is, again, the use of duality. So here, we basically used, implicitly we used the theorem from topology. In 2 dimensions, so suppose you have a rectangle, and suppose you draw one continuous path from left to right, and you draw another path from top to bottom. These 2 paths have to cross each other. This is a theorem from topology that we have used to justify the duality here. But there's a little bit thinking which is required to get what I'm going to tell you next. You may just choose to trust me during the talk. So basically, what is the special role of 1/2? Why 1/2 is so important, it's so special, and serves as the critical threshold? That's because 1/2 is exactly the point that the probability of being closed and the probability of being open are the same, so that you can couple the original model and the dual model together so that when 2 edges are dual to each other, one is closed if and only if the other one is open. And through this coupling, and also using the sort of topology theorem I just told you, and using a little bit trust on me, we see that if you can find a green crossing from left to the right, if and only if there is no red crossing from the bottom to the top. Those are the if only if. And then combining these things together, we see that the crossing probability is 1/2. Still, this does not quite prove 1/2 is the exact threshold, but this gives a strong hint. because this is exactly the point that the probability to cross through a square box is away from 1 and also away from 0. And finally, this was proved by casting in 80s using some more ingredients, which I'm not going to talk about. Now you see there is this simulation, which shows that as the P increases, how the open clusters in the percolation model evolves. If you have good eyes, you'll see that near the criticality, near P equal to half, there is emergence of a macroscopic cluster. If you don't have good eyes, I have the 3 screenshots to show you here. The first picture shows what happens at P equal to 0.4. You see there's only a very small open cluster. You can barely see if you sit at the back. Now, the second picture, when P is equal to 0.51, already there is a very obvious macroscopic cluster. And when P is 0.55, the macroscopic open cluster is basically dominating everything. So this says there is a phase transition. What do I mean by phase transition? We have a physical system, and there's, in this case, there's one parameter, P here, we can adjust. Phase transition basically means, well, when you adjust the parameter just a little bit from below criticality to above criticality, then the macroscopic property of the system changes dramatically. Like here, you would change from no infinite open cluster to there is infinite open cluster. In fact, not only we have a phase transition here, the phase transition here is also sharp. What do we mean by sharp phase transition? It basically means that in the entire subcritical regime, that is, as long as P is strictly less than a half, not only you do not have infinite open cluster, but if you look at the open cluster of the origin, it tends to be very small. The probability for this to grow to into a large cluster decays very quickly. Actually, it decays exponentially. So we have a sharp transition for Bernoulli percolation. After describing the phase transition, now let's move to critical phenomenon. So a natural question is, at criticality, what happens? At criticality, do we have an infinite open cluster? This turns out to be a challenging problem. We know the answer for 2 dimensions and also for high dimensions. For high dimensions, that's because, according to physicists, if the dimension is high, then we are sort of in the mean field, so-called mean field regime, where 2 particles basically interact with each other in the same manner. The geometry does not play an important role, which is why we have the sort of mean field behavior, which is easier to analyze. Although to rigorize this is not easy at all, mathematicians have developed powerful methods like Lace expansion to deal with the high dimensional behavior. But the most interesting behavior in lower dimensions, especially for d equal to 3, remains a major open problem in this field. Now, suppose we know the water can actually pass through the material. What are the other questions we would care from a physics point of view? I guess one natural question is, how much time does it take, right? How long does it take for the water to flow through the coal, for instance? Mathematically, this would correspond to the random metric generated by the shortest open path. In this simulation, we see the evolution of the metric ball. This is in the supercritical regime when P is like 0.51. Basically, I think we can more or less see from the animation that in this case, the random metric is linear in the Euclidean metric. The challenge here is to understand something like the limiting shape of the metric ball and also the fluctuation, that is the second order term, what is the order of variability for the distance, and also how much would the geodesic fluctuates from the geodesic when you are just in the original lattice. Those are also very hard problems. We can also ask what happens at criticality. Here is another simulation, again describing the evolution of the metric ball. You see that in the critical case, very vaguely, there is some fractal structure. Although we don't have much mathematical progress on this front, we do have some results that can justify the fractality here. For instance, in high dimensions, we know the distance grows as the square of the Euclidean distance. And in 2 dimensions, we know that if you look at the geodesic in this metric, its Euclidean dimension is strictly larger than 1. This is due to Eisenman-Burchard and as well as the sort of ISW estimate. Okay. In these models, we assumed that particles only have nearest neighbor interaction, or basically only nearest neighbor edges can occur. This is probably true in some physical systems, but certainly will not be correct in some other physical systems. It would be more natural to think, even though when 2 particles are sort of away from each other, they would still have interaction. It's just the strength of the interaction should decay in terms of their distance. So to incorporate this, people proposed long-range models, and in particular, long-range percolation models, where you could have a long edge joining 2 vertices that are far away from each other. It's just the probability is very small. I don't want to tell you too much about this model. I would just say there is also a very interesting and intriguing phase diagram for this model. And at criticality, we have obtained some scaling limits results for the random metric. Another type of question that you would be possibly interested in is random walk on the open clusters of percolation. It is probably one of the few most fundamental results in probability that random walk on regular lattices, they scale to the Brownian motion, which is the random movement, the random dancing of a pollen observed by Brown. If you observe the pollen particles in the water, they have all sorts of collisions from the water, and which results in this very highly irregular motion, and people call it the Brownian motion. And then it is very natural to wonder, in this percolation clusters, do you still have scaling limits of Brownian motion for the random walk? Especially at criticality, this is a major challenge. We obtained some preliminary results along this direction for long-range percolation, but we wouldn't be able to solve the question at this point. Okay. Now, I mean, up to now, I'm talking about Bernoulli percolation, where edges are independent of each other. But you could imagine there were other scenarios where there should be some correlation, right? So that's what I'm going to talk about now. You would think if things are correlated, you have to put some nice structures. On the one hand, it corresponds to some nice physics models. And on the other hand, this nice structure allows you to do some interesting mathematics. If the structure is too arbitrary, I don't believe anything interesting can be said. So one model that we can choose to talk about, and which is also a very canonical model in statistical physics, is the Ising model. In this video, it shows a small experiment on when you hit the magnet using a march, then the magnetization will be weakened and eventually lost, and then this hanging nail will drop off. Wait for 10 seconds, it will drop off. This says there's a phase transition in terms of temperature for the magnetization of the magnet. The 2 simulated pictures also echoed this point. On the top, this is a picture simulated for high temperatures. You see that there's all these chaotic colors. This basically corresponds to no magnetization. And on the bottom picture, things are pretty organized. It's one color on the top and the other color on the bottom. There's some fluctuations. This is very ordered, and this corresponds to magnetization. Now, how do this organized and not organized corresponds to magnetization exactly? Basically, we can imagine at every lattice point, there is a dipole. The dipole can have 2 directions. It can point to the north or point to the south. If the directions are chaotic, then they are basically the combined effect is canceled with each other, and you do not see macroscopic magnetization. On the other hand, if things are pointed to roughly to the same direction, you see there is a macroscopic effect. In order to understand the important role of temperature in this phase transition, we need a little bit more definition for my time is almost up? Not yet, okay. The clock says otherwise, but the chair asked me to continue, so I will continue. Sorry. Let's look at the math definition of the Ising model. So let's say each vertex has two spins, either plus or minus, it's like red or blue. And we just need to understand what is the probability to have assignment of colors, right? For each configuration, the probability is proportional to exponential of the number of agreeing pairs divided by t. So from the definition, you'll see that the model prefers to have the same color for nearest neighbor spins. And if t is smaller, this sort of preference is stronger. And this hence, there is a phase transition in terms of t, in terms of the temperature. But to prove this rigorously still requires more work. And this was done by Peirce in 30s in his very classical work that shows that in 2 dimensions and above, there is a phase transition for the Ising model. After understanding the phase transition, we can also ask, what about the critical phenomenon? At the critical temperature Tc, what do we expect? Is there supposed to be mechanization? The answer is no for all dimensions. And in the most important case for d equal to 3, this is a result obtained about a decade ago. Now I will take the chance of Ising model to explain what would happen if we have noise or disorder in our physical system. Because when we pose a physics model, we have made various idealized assumptions. However, usually the environment cannot be as idealized as we think. There will be all sorts of noise in the system. So it would be important to understand, if you have some noise in the environment, would this drastically change the property that you are interested in? So there are a few ways to introduce noise to Ising models. One way is to say, okay, let's have a random external field. That is, at every lattice, we have a random preference to plus or minus independently. We want this preference to be weak. Otherwise, you can imagine that the property of the original model will be completely destroyed. So here's some simulation. The simulation goes as follows. We simulated a very natural evolution of the Ising model. It's called global dynamics. Not only this is a very natural way to sample a Ising model, but also this corresponds to the natural process for the Ising model to relax to the equilibrium. In all the 3 simulations, we started from all plus. And the noise is increasing from left to the right. Basically, if after a long time of this simulation, plus is still the dominating direction, then you imagine there should be mechanization. Otherwise, the mechanization will be destroyed. Then we can see clearly that in the 3rd simulation, it becomes chaotic very soon. That probably means, okay, large disorder would destroy the mechanization as we expected. The more subtle question is, what if we have weak noise? From the simulation, it seems to suggest the mechanization will be preserved, even if we have very weak noise. But, here is a but. The simulations can be misleading for 2 reasons. One is that the time is too short. 2 is that the scale is too small. So this is where the physicists have debates and where mathematicians have clarified the debates and even found a phenomenon that elusive to physicists using rigorous methods. I see the chair is about to stand, and I think that suggests my time is up. I would just say there are many other things I didn't have time to tell you. There are other ways to introduce noise to the Ising model, which one of them is supposed to model the avalanche, and also there is yet another important population model coming from level sets of coming from a certain Gaussian process. There are some beautiful simulations. At least you got the impression that this subject has a lot of interesting and rich questions that I hope some of the youngsters in the audience can be attracted to. My time is up, so I'm just finished here. Thank you so much.
Thank you, Professor Dean, for your wonderful speech. Actually, I would hope that you would actually continue to talk, but we have a very tight schedule. And first, I would like to say that actually I really enjoy your talk, and your insight into population and static physics is truly enlightening and highlighting the intricate interplays between probability and physical phenomena. Please allow me to introduce our second speaker, Professor Yifeng Liu, from the Institute for Advanced Study in Mathematics, Zhejiang University. Professor Liu, Ramanujan Prize laureate, is renowned for his work in algebraic number theory, algebraic geometry, and automorphic forms. His talk, titled From Natural Numbers to Infinite Categories, we explore how the phenomenon of abstracting has led mathematicians from simple concepts like the natural number to the complex one like the infinite categories, emphasizing the necessity of such abstraction. Let's welcome.
Okay, thank you very much. So first, I would like to thank the committee to give me this wonderful chance to share some mathematical thoughts from old to new to the audience. Okay, I will, sorry, how to turn up and down? Okay, how to go back? I'll go back to it. Okay, thank you very much. Okay, so I will start from some mathematics that everybody knows from childhood. They are so-called natural numbers. Okay. So this is also the order where human beings started to, how mathematics started from. Okay, so about 50,000 years ago, mathematics started from the so-called counting, and there are many ways we count. Today we use numbers, but numbers are some artificial things, right? We write 1, 2, 3, but those are invented from later. And at the very beginning, people use objects to count. For example, use sheep, stones, and knots, and even ceramics and ceramic objects. And today we don't use sheep, stone. We eat sheep, right? We play with, but we don't count in sheep unless you feel hard to sleep. So today we use this so-called Arabic numbers, 0, 1, 2, blah blah. Okay, those are called natural numbers because they came from the nature, like sheep, stones, and knots. Okay. And actually, the generation of this concept of numbers, those abstract numbers, is one of the earliest mathematical thoughts people discovered. In today's language, it's called one-to-one correspondence. Also, today we use like a 10-digit enumeration. Like we count to 10, then we use 11 and 1, 10 plus 1, 10 plus 2. And also, if you know French, you know that they don't count in this way. But anyway, this is called a system of numeration. Today, we commonly use the 10-base one. And in computer science, people use the 2-base one. Okay, these are some pictures I found from internet. I apologize if there's some copyright issue. So the first one is the counting by knots. As you can see, there are characters, right? So you can imagine this was from ancient China. And the second and the third are from ancient Mesopotamian. They're counting from, they use ceramic objects to count. And you can see on the third picture, there's symbols, and they look very like from the second picture. So that's one source of this abstract notion come from. They came from actual objects. And the last picture, I think it's from ancient Egypt, right? They use different objects to represent a certain amount of number. And you can already see there's an idea of 10 10-base sort there. There's a 1, 2, or the 9. Then 10 is, it just changes to another symbol. Then 100, it's even bizarre. And then 1,000, there's something there, right? And until 1 million, there's a human being. Okay. So these are all early sorts, mathematical sorts from all Asian civilizations. Today, we know that there is actually a hierarchy of numbers. We start from natural number, and then we want to present their ratio, represent their ratio. For example, the ratio of female audience to male audience in this room, like some to something. And you know that in many cases, this number is not a natural number anymore. It could be like 2 to 3. Okay, 2 to 3 is not any natural number. The ratio of natural numbers are called rational numbers because they are ratios. Okay, they are ration. Okay, and then there's an important discovery that at about 2,000 years ago, the ancient Greeks thought that every quantity in nature can be represented by a rational number, and certainly that's not true. The first example is that if you consider a right-angle triangle, like a two right sides are 1, 1, then the other side should be square root of 2, and that number is not rational. So that's called irrational number. And that discovery was thought as the first crisis in mathematical history. And later, people even found a way to classify these irrational numbers. And some irrational numbers can be represented as a root of a polynomial equation with integer coefficients. That are called algebraic numbers, and some are not. And irrational numbers have also other type of, for example, today we know that there are something called the real numbers. There is a real line, and the rational numbers are dense there, but they don't fit all the holes there. So there's this real number, and real numbers basically, all numbers we see from our daily life can be represented by a real number, but they don't really give all the interesting numbers. Okay, and for example, if we want to solve the equation x squared plus 1 equals 0, there won't be any real number satisfying this equation. So you need to extend the number system to something called complex numbers. Okay, as of course these numbers are more complicated than the real numbers, so that's called complex numbers. That's how I understand this terminology. And in modern physics, people have in some sense proved that complex numbers are actually necessary in describing our universe. Okay, okay, now I will continue to introduce a second main origin of mathematics. Okay, so mathematics also starts from geography. Okay? So what does that mean? Okay, for example, from long time ago, when there's a human being, there's an animal, they travel, right? They need to move from one spot to another spot. When you do this, there are many choices. You can go from this way or that way. There are even change of ways. But this is called from points, and there are past linking points. So there's a very famous problem in mathematics from 18th century that's called the Königsberger 7 bridges. So you see in the picture, there are 4 pieces of lands, right? Two are lands and 2 are islands. And there are 7 bridges linking these pieces. And how many ways you can travel through all these 7 bridges, and what are the shortest ways? And those are basically the question you can consider. And this is also a very important origin of mathematical study from this geographical question. And from all this consideration, there's a new branch of mathematics studied. It's called the topology. And the official terminology was actually invented by Leibniz in his book called Geometria Situs in 17th century. Okay? And in topology, there's a very important concept called homotopy. This word probably non-mathematician didn't hear about this. What does this mean? This essentially means deformation of path. So what does deformation of path mean? Let's think about this. We're now in Kowloon, right? I mean, if we want to travel from here to the island, if we drive, how many ways can we do? There are 3 ways, because there are only 3 tunnels under the Victoria Harbor, right? But if you want to swim from if you want to swim from Kowloon to island, how many ways? There are infinitely many, right? You can choose any starting point, go any route. If you want to challenge yourself, you can go S, right? Or you don't need to go straight, right? And you can land at any point on the island. So there are infinitely many passes from point Kowloon to point island, okay? And I can swim this route today, and tomorrow I just shift a little bit to the east of the previous route. That's the second route. And the day after tomorrow, I can choose a little bit even easter to the previous one. So this deformation, this is infinitely many choices, right? There are infinitely many choices. There's no way that you can drive like this. There's only three tunnels. There's no way I can shift or deform my way of driving. So this is an important concept from topology called homotopy. And at this point, probably you won't see any relation between natural numbers and this homotopy. But I think in late 19th century, there's a new subject somehow relating these two very different sources of origin of mathematics together. That's called homological algebra. So later I will introduce a little bit, and I will also mention this, the modern, the very recent development in this subject, the so-called infinity category theory. Okay, here's a picture. You can view X as Kowloon and Y as the island. And so gamma naught is the way you swim on your day 0, and the gamma 1 is the way you swim on day 1000, for example. And in the middle, you can just deform gradually day by day as you wish. Okay, so here are even more bizarre words, right? What J comes as homomorphisms, homotopies. Okay, so here comes a very important branch of mathematics, or you can even call this a philosophy of mathematics, but algebra. Okay, we know algebra, right? We study algebra even from elementary school. But the term algebra in modern mathematics is a little bit more abstract than the algebra the general audience know. Okay, so this is a key. This is a subject where you can really feel the abstractness of mathematics. So I will take one example of the objects we study in algebra called a abelian group. So what is an abelian group? So first, it is a set. A set is just a collection of objects, okay? And there's an algebraic operation on this set, which is a binary one, okay? I denote this by a plus. Okay? It is, of course, related to the plus we are all familiar with, but this is an abstract version. So what is plus? Plus is an assignment from A times A to A. This means that given me 2 elements in A, I will give you 1 element in A. Just like what usual addition does, right? Usual addition, you give me 2 numbers, I give you 1 number, which is the sum of the 2. And this addition should satisfy what an addition should satisfy. So first, it should satisfy the associativity law. If you add x plus y first, then add z, it is the same as you add y plus z first, then add x. Okay? The second is the commutativity, which means that the order doesn't matter. If you add x plus y, same as y add x. The third one is that there is something called a 0 element. There is a necessarily unique element 0, such that 0 plus x is x. So here's a very good exercise. Even you never heard of this, you can still do this exercise from pure logic. Why 0 is unique from this definition. Okay, you only need the logic. There's nothing you really need to. And there's also something called inverse element. So for any element x, there exists also a necessarily unique element called the negative x, such that when you add x and the negative x, you get 0. Again, this is a pure logic exercise to see why inverse element must be unique. So what is a homomorphism? Homomorphism, okay, what does this word come from? Maybe from Latin? I'm not sure. Okay, a homomorphism is a relation. It is something between two abelian groups it is a map F from A to B that respects the addition, which means that if you add them first, then you map to B. It's same as you first map to B, then you add them together in B. So you see two plus signs here, right? They actually have different meanings. The plus sign on the left-hand side is the addition on A, and the plus sign on the right-hand side is the addition on B. Okay? That's a homomorphism. And again, that's a pure logic exercise to prove that a homomorphism must send 0 element to 0 element, and then must send inverse element to inverse element. Okay, examples. The numbers, so we have introduced in the first slide, they all form abelian groups. And what's the addition? They are just the usual addition of numbers. Like giving me two complex numbers, 1 pi, 1 I, then the sum is just pi plus I, right? And that's just a complex number. And the next example is a little bit more interesting. Actually, you can use multiplication to form the addition in a group. I know it sounds weird, but that's how algebra works. So in fact, if you remove 0 element from Q, or you remove 0 from R, or you remove 0 from C, they also form abelian groups. But now I take multiplication instead of addition to be the addition of this group. You may feel strange because, okay, you just said there should be an element called 0. Then you remove 0. What is that about, okay? Because under multiplication, the role which the abstract 0 play is now played by the number 1. Because 1 multiplied by anything is that thing itself, right? Okay, so that's how algebra works. They borrow some familiar notation and they make it abstract. And after some day, you don't recognize this anymore. That's how, especially a feature of modern algebra. Okay. Now, okay, let's continue with this notion. So we have abelian groups. Let's make an example. Okay, so some examples of abelian groups, which are not just from numbers. So remember, in the previous Königsberg 7 bridge problem, I want to define some algebraic notion from this geographical problem. So I define something called A0. That is an abelian group. This abelian group is freely generated by 4 pieces of land, in which 2 are islands. So what does this mean? What does freely generated mean? This means that A0 is just 4 copies of Z. Each Z represents one land. So elements in A0 is like a weighted sum of 4 lands. Like I put the north land a number 1, and I put the south land a number -1, and the left island a number -3, the right island a number like 2. That's an element in A0. That's called a abelian group freely generated by 4 pieces of land. And I also have 7 bridges, right? But each bridge have two directions, right? In ancient time, there's no one-way road, okay? So you can travel from this way or the other way. So if we count the directions, there are 14 bridges with directions, okay? So you have 14 bridges, and I let A1 to be the abelian groups freely generated by these 14 bridges. And more importantly, I have a homomorphism from A1 to A0. So how does this work? So you see, if I take the upper rightmost bridge, and there's a direction, let's suppose the direction is from the land to the island, okay? Then the homomorphism D will send this oriented bridge to the element A0, that is its destination minus its origin. So this is 1 times the right island plus -1 times the north land. Okay, so that's the homomorphism that's given. It's called a D. And this homomorphism actually will play an important role in solving this, the original, the underlying topological problem of this 7 bridge. So there's an even more abstract notion of this example called a chain complex. And this chain complex, we even consider an infinite chain of homomorphisms, like in this example. So rigorously speaking, a chain complex of abelian groups is a sequence of homomorphisms of abelian groups like this. From A, you can have infinite many indexed by integers, rather all the way remote from then to A2, A1, A0, A negative 1. Okay, so the previous example is just one instance of this chain complex where you only have 2 non-zero terms, A1 and A0. All others are just the zero group. And we require this homomorphism to satisfy the following condition. So if you compose, so if you go from A2 to A1, then you go from A1 to A0. If you pick up an element in A2, you first go to A1, then you go to A0, that element must be 0. Okay, that means the composition is the 0 homomorphism for every n. So this chain is called a chain complex in algebra. Okay, so we already have this analog of points like the chain complex. And what is the analog of road or path for this chain complex? Of course, there's a homomorphism of chain complex. This is relatively natural to define. The homomorphism of two chain complex is just a homomorphism at every stage. Okay, at every stage. At every stage n, you have a homomorphism Fn from the group An to Bn. And the whole diagram should commute, which means if you pick up some element in A2, you go to A1 first, then you go to B1, should be same as you go to B2 first, then you go to B1. Okay, that's a homomorphism. So what's the analogy of homotopy? That is a very sophisticated, and that is one of the most important definitions in algebra. So a homotopy from between two homomorphisms, or from one homomorphism F to G, is a diagram like this. Okay? So it is a system of homomorphism from A0, but not to B0, as to B1. Okay, you like shift one thing to the left. So why is there? Okay, so what does homotopy mean? Homotopy, in the previous example, we know that homotopy are deformation of paths. Okay, so path is one-dimensional, right? So deformation is somehow two-dimensional thing, because it's you swipe through or the Victoria Harbour, you get some two-dimensional thing. So in some sense, this homotopy will raise the dimension by 1. So that's how you do get something that is shifted degree by 1. Okay, that's the thing called a homotopy. And so there is a unifying concept called a category, which put all these different sorts from algebra and topology together. So I will not give a definition of category. That's way too abstract. So I will give an analogy instead. So recall that, a path in mathematical language can be regarded as a map from a particular space, which is a closed interval of 0, 1 to a space. So from this remark, you can see that in topology, we have spaces, right? Okay. And maps and homotopies, higher homotopies. And in algebra, we have the corresponding concepts as well. And there is something unifying them called a category. We have objects, morphisms, two morphisms, and so-called n-morphisms. And, okay, so since I don't have much time, I will say that this category is where non-trivial higher morphisms are some objects just recently developed in the recent 10 or 20 years and vastly become very, very important in many mathematical, so it has lots of growing influence in mathematical research. I will give some examples. The first, it has played big role in its origin called algebraic topology. For example, computation of homotopy groups by Wang Guozheng and Fu Dan and Xu Zhouli, two Chinese mathematicians, very young, both younger than me. And also in algebraic geometry, for example, the development of the modern six-operation formalism by myself and Zheng Weizhe, and Gatesbury Rosenbrim and Lucas Mann. And also in arithmetic geometry by Bart Schalter in this p-adic geometry. And also in representation theory, the so-called geometric long lines, which will be mentioned in the next talk by Professor NAKAJIMA. And also in number theory. And it also generates some new mathematical areas like derived algebraic geometry and motivic homotopy theory. Okay, I will stop here. Thank you.
Thank you, Professor Liu, for your wonderful speech. Your exploration of the journey from the natural numbers to infinity category were both profound and engaging, shedding light on the beauty of mathematical abstraction. Please allow me to introduce our third speaker, Professor Hiraku NAKAJIMA from the Kavli Institute for Physics and Mathematics of the Universe, the University of Tokyo. He's also the president of the International Mathematical Union. His research focuses on geometric representation theory and the interdisciplinary field between geometry and algebra. And he has received numerous awards, including the American Mathematical Society Co-Prize in Algebra in 2003 and the Japan Academy Prize in 2014. His speech will focus on the 3D quantum field theory and the long-length duality. Let's welcome.
So how to use? So I'd like to talk about the 3D quantum field theory and the Lagrange duality. Okay, thank you. So Lagrange duality is one of the central problem in mathematics, and recently there's some big achievement still announced, so the proof must be checked. But anyway, so this is one of the very important problem in mathematics. And on the other hand, 3D quantum field theories, this is more precisely, I will talk about the three-dimensional supersymmetric quantum field theory. This is a subject in theoretical physics. And the theoretical, as Professor Dean mentioned, that theoretical physics has no mathematical rigorous foundation, but nevertheless, they have give some insight to the to new phenomena. In particular, I'd like to talk about this insight to give some new hint about the some aspects of Lagrange duality, which I really want to mention. And I'm working on the mathematical rigorous justification of 3D quantum field theories, and of course I know because Lagrange duality is a central problem, so I have some basic knowledge, but I never imagined that my research is something to do with Lagrange duality. So this is the reason why I'm so excited recently, so I'd like to share with you this excitement. So anyway, so this Lagrange duality and the 3D quantum field theory are very different subjects. So finding new relations between the two seemingly unrelated subjects are very exciting, and that I want to emphasize. Okay, I must say a little bit technical jargons, but I hope that already you heard about the categories, so I hope most of you accept them. So anyway, so you have input for the Lagrange duality. So this is C and G and G check written there. So this is Riemann suffix and complex reductive group and Lagrange dual group. So anyway, so you have this is the input, C, G, and G check. Then from them, you can construct two categories. So there's one category is called automorphic side, and the other category is called Galois side. I will not go into the detail of this definition. Anyways, this is technical. So you have, from the input C and G check, you can assign two categories. So they are very different. So there's absolutely no relation between them, but nevertheless, they are given from the same input from C, namely C and G check. Then Lagrange duality predicts the relation between those two categories. So as I said, these two are seemingly very different. If you have some relation between them, then it is very exciting. And because this is so exciting and this is so powerful, for example, the famous proof of the Feldman conjecture by wires is used this kind of idea. Okay? And I mentioned the categories, but in the number theory, which for the application to the number theory, so people use the slightly different version of the Lagrange duality. So in that case, you replace categories by more concrete objects. So Professor you mentioned that the category is the most abstract notion in mathematics, but you have lower level abstract object called vector spaces. And so you, from input C and G check, more precisely, you need to replace C by some more number theoretic object. This use the so-called Bayes-Rosette strong. But anyway, so from the same input data, you produce two vector spaces which seemingly very different, but nevertheless, Lagrange duality, arithmetic Lagrange duality predicts some relation between them. So because of this seemingly unrelated objects are related, if this is established, this is very exciting and this is very powerful. Okay. So this is Lagrange duality. And you consider this 3D quantum field theory is related to the so-called relative Lagrange duality, which is, in fact, proposed very, very recently, Ben Zibisake-Ladrich and Ben Katish. So this is more than 200 pages. I don't remember the number of pages, but it is posted in the archive as a preprint. So in this case, instead, so you put C is the same. Maybe I turn back. So the input data is C and G check. Now I put instead of G, I take G1 and G2. So then, because we have two different inputs, I can assign four categories. For G1 and G2, for G1, you have two categories, as I mentioned. And for G2, I also have the category. So you have, in total, I have four categories, right? Four seemingly different objects. But those categories have some interaction between them. So this interaction is given by the so-called, this is the space M. So this is the so-called Hamiltonian G1 times G2 space. I will not go into the detail, but so those four categories are related, first of all, so maybe go to the next one. So I have four categories, and horizontal arrows is a prediction from the geometric Lagrange conjecture. But there's interaction which goes in vertical directions. So this M, so this gives an interaction between two categories. And so because the Lagrange duality predicts equivalence in the horizontal direction, so if you have the interaction in the vertical direction in the left side, you also predict the similar interaction in the right side. So this is a red interaction and light interactions. And because of the duality, so this interface interaction are given by different sources. So this is one side. For the red, you use this space M. But for blue interaction, you need to use different different space, M check. And Lagrange duality, relative Lagrange duality predicts two interactions which commute with the Lagrange duality. So this is the message of relative Lagrange duality. So as I said, the input data is C and G, and here I replace G by pairs, G1, G2, but I still keep the C to be the same, and this relative Lagrange duality should hold for any choice of C. So if you replace C, then you still have the similar. And in this case, the M and M check is independent of C. So that is the relative Lagrange duality predict. And so by this way, you can explain various known examples. So I started with trivial examples, which is some standard space M and M check. And there's the so-called Whittaker model, which has been studied in this Lagrange. And also there's some known example which cannot be explained in this way. But so there are lots of interesting examples. Maybe I should also say that this kind of relation between the four categories is called functoriality in Lagrange program. So this functoriality is one of the most important theme in geometry in Lagrange program, Lagrange duality. Okay. Then, in fact, this relative Lagrange relative duality has an origin in theoretical physics. So it is started from the work of Kapustin and Witten in 2007, and also its subsequent work by Guy Otto and Witten, 2009. So they propose a way to understand geometric Lagrange conjecture by theoretical physics. As I said, this is, in fact, this is a four-dimensional quantum field theory instead of three-dimensional quantum field theory, which I mentioned. It takes I mean, as I said, the quantum field theory has no mathematical rigorous foundation. And at the same time, for mathematicians, it is not so easy to understand what physicists say, because they usually use very different languages. And as I said, they are usually not rigorous. So it will take many years, so about more than 15 years, maybe no less than 15 years, certainly more than 10 years to understand for mathematicians to understand what those physicists say. So anyway, we now understand that those M and M check are coming from the so-called three-dimensional quantum field theory. So three-dimensional, because, as I said, Kapustin and Witten used four-dimensional quantum field theory to explain Lagrange duality. I don't explain why four is four-dimensional quantum field theory. There's some trick there, but anyway, so three is, if you have four-dimensional object, and if you have some boundary in the four-dimensional object, then it is a three-dimensional object. And the three-dimensional quantum field theory appears as a boundary of four-dimensional quantum field theory, which Kapustin and Witten use to explain the geometric Lagrange. So anyway, so you have definition of M check from M in three-dimensional quantum field theory. But as I said, this three-dimensional quantum field theory has no mathematical rigorous foundation. So this requires some justification, mathematical justification. Unfortunately, for this three-dimensional quantum field theory, I have been working on for several years. And in particular, so this is the Lagrange duality, and this aspect of duality understood in my work with Braverman and Finkelberg. So we can somehow use our understanding to understand, to attack mathematical rigorous foundation of what this Guy Otto and Witten answers for how to define M check from M. And at least in some cases, we can we have a proposal for M check starting from M. I should not go into detail, but we have some concrete examples, which is rather striking because, so we maybe, yeah, I should not go so much into this, but so I have some concrete example of M, and I compute M check, and I have another example of M, and I compute maybe M, I said M1, from M1 I compute M1 dual, and from M2 I compute M2 dual, and in fact, by our method we computed the dual, and we found that M1 check and M2 check are the same. So starting from different spaces, and we apply our method to compute the M check, then we find the same space. This is in fact contradictory to what we can expect, because this Lagrange duality predict duality means that if you can go from one side to another side, then starting from another side, you should return back to the original space. So if you consider M starting from M and compute M check, and if you start from M check, then you return back to original space M. But our examples somehow contradicts this expectation. And the Benzibi and others formulate the relative Lagrange conjecture as a duality. So M check of, if you start with M check, then you should return back to M. So this is contradictory, but in fact, it's not the mathematical contradiction. In fact, they impose some conditions on the starting space M, starting interface. So our example doesn't satisfy this assumption. So this is, I think this is a exciting sign, which means that somehow the relative Lagrange proposed by Benzibi and others are not sufficient to understand all the examples which we do have. And in our case, maybe we should more seriously consider our proposal so that we can recover this duality. So anyway, so I finish with my, oh, let me go. No, so still I hope it. So this is the most exciting part of myself. I propose many questions, and this I hope that I will see some advance in future, and that's the reason why I'm so excited. And this is, I mean, of course, you want to finish earlier, but. So anyway, so the question first is, I said I have some assumption to define the dual space, and so we need to drop those assumptions. And the three is, as I said, this is still we don't understand. So M, starting from M, we should get M check, but then from M check, I should return back to M. So this is somehow very, very non-trivial if I under our recipe to define M check. So this is one of the most mysterious part. And finally, as I said, this should connect the Lagrange duality. And so far, we just understand the superficial level interaction between M and M check. We still don't know why this is compatible with Lagrange duality. This is the most deep question, which I hope to understand in near future. So thank you very much for attention.
Thank you, Professor NAKAJIMA, for your wonderful speech and your explorations of the really fascinating, unexpected relations among the different areas of the mathematics, the automorphic side and the Galois side, and between the mathematics and the physics, and also the quite unexpected connection to the first two talks. That's really exciting. Please allow me to introduce our last speaker, Professor Efim ZELMANOV from the Shenzhen International Center for Mathematics at the Southern University of Science and Technology. A Fields Medal laureate, Professor ZELMANOV is a distinguished member of various academics around the world. So he will present his talk on Galois and communication technology, offering a unique perspective on the historical impact of Galois' work on the modern communication technology. Let's welcome.
Well, I won't talk about the most recent work. Let us go back about 200 years ago. Now, how do I? Okay, this one. Okay, this is supposed to be the portrait of Évariste Galois. This is an amazing story. The guy was a French teenager who did not have any formal mathematical education except high school. He failed entrance exams to the university twice. People who knew him later wrote that it happened because he understood mathematics much better than his examiners and was not smart enough to hide it. He was killed at the age of 20 on a duel. Before that, he wrote a mathematical paper and sent it to French Academy. You know, he was a great mathematician. He had no idea how to write papers. Okay. And since he did not have any illusions about his ability to shoot, and he could predict the outcome of the duel, the night before the duel, he wrote a very detailed mathematical letter to his friend. And one of the top mathematicians of the 20th century, Hermann Weyl, called this letter the most influential mathematical paper ever. This letter and the paper that he sent to French Academy, nobody would be able to read them. And here a lot of credit goes to Liouville, who was mentioned in Professor Ding's talk. Liouville was able to decode Galois' works. Okay, and by the way, this portrait hangs in all mathematics departments, but this is artist's imagination. Nobody knows how Galois looked. Who would make a portrait of that strange teenager who is not interesting to anybody? At that time, there were no selfies. Okay, so what did Galois do? I'm pressing, and nothing happens. Please help. Oh, I'm pressing the wrong button. Okay. Depending on when you finished middle school, you may still remember the formula for roots of a quadratic equation. There exist similar formulas for equations of degree 3 and 4. Nobody remembers them, nobody uses them, but they exist. And for many years, people tried to find similar formulas for equations of degree 5, 6, and so on, unsuccessfully. And then they started to suspect that maybe these formulas do not exist. The first credible attempt to prove it was done by Paolo Ruffini. But his proof contained a gap. And we know that a proof with a gap is not a proof. All his life, he tried to patch this gap unsuccessfully. The first correct proof that similar formulas for equations of degree 5, 6, and so on do not exist is due to another young genius who died young. Oh, well, I don't know if you can see. What is that? Niels Henrik Abel. So what did Galois do? Galois explained what was going on, building on ideas of Lagrange. And now Lagrange wrote a very influential paper. He analyzed all existing formulas, and he showed how these formulas depend on symmetries of roots. Symmetry is a very basic notion. Everything has a symmetry. Whether, you know, this wooden thing or ornament in Alhambra, and symmetries can be performed one after another. It's like a multiplication. Symmetry is some transformation of the system that kind of takes it to itself. Symmetries can be reversed. You know, the concept of symmetry is codified in the mathematical area which is known as group theory. You already had a crash course in abstract algebra in Professor Sliu's talk. So I will assume that you know what is a group. If you go to a deserted island and you are allowed to take only 3 mathematical concepts with you, give a consideration to the concept of a group. So Galois showed how the question whether a root can be expressed by radicals depends on the groups of symmetries of this equation. He asked the right question: what is a group of symmetries? So when in the 20th century physicists started to study elementary particles, they knew which question to ask. I heard the following phrase from Sheldon Glashow. He's a Nobel Prize winner in physics, one of the fathers of the universal model. He said, "I don't know if God exists, but if he exists, then he knows group theory." Okay, but Galois did 2 things. He worked on solution of equations in radicals, and there was a second theory that he developed. He introduced finite fields. I must say, well, I understand why Galois was interested in solution of equations and radicals. At that time, everybody worked on that problem. But why finite fields? I have no idea. You know, Schopenhauer, a German philosopher, said that a talent hits a target that nobody can hit. A genius hits a target that nobody sees. I will give you an example of a finite field. Let P be a prime number. You know, I'm addressing most not professional mathematicians. I was told that there are high school students here, so you are my excuse. Let P be a prime number. Every integer can be divided by that prime number with a remainder. And the remainder runs from 0 to P minus 1. Now I will show you how to add and multiply these remainders. Let P, well, be equal to 5, for example. So there are 5 remainders. 0, 1, 2, 3, 4. Take 2 of them. We want to add them. If the sum is smaller than P, okay, be happy. Then that is a remainder. But if the sum is bigger than p, it cannot be a remainder. Okay, divide that sum again, and the remainder of this division is declared to be the true sum of these two remainders. Similarly, you define multiplication. For example, if p is equal to 5, then 2 plus 4 is equal to 1. Why? Because 2 plus 4 is 6. Divide 6 by 5, the remainder is 1. Similarly, 2 times 4 is equal to 3. Now, this is the first example of a finite field of Galois. Why did he do it? We know real numbers and complex numbers. We were told even that complex numbers are appreciated by physicists. These real numbers and complex numbers can be added and multiplied, and these operations are subject to certain rules. You can even divide by non-zero numbers. And the addition and multiplication of remainders that I described above satisfy all the same properties. They are also subject to the same rules. When I was a student, unfortunately many years ago, we were told that real world are real numbers and complex numbers. Only strange algebraists and number theorists can be interested in Galois finite fields. Okay. No, since then there were some changes in the world. The first application of finite Galois fields. Suppose that we send a satellite to another planet or whatever. That satellite sends a signal to the Earth. The signal is a sequence of zeros and ones. 0 and 1 are remainders modulo 2. So they are elements of the finite field of Galois of two elements. Those of you who had a course of linear algebra know that n tuples of elements form a vector space. You can add them. So a signal is an element of a vector space. But unfortunately, while it goes to the Earth, there are noises. So what you get is not what was sent. What should we do? The following scheme was invented in late 50s, early 60s in Bell laboratories by Shannon, Hamming, and so on. It's coding theory. We decide on the Earth that we will send signals only from a certain subspace, which is called the code. If we got a signal that does not lie in that subspace, okay, it means that there was a mistake. So what do? You choose the closest element from that subspace and say maybe that was the intention. Closest, in which sense? It means that you need to define some distance. We define the so-called Hamming distance. Given two n tuples, the distance between them is the number of positions where they don't disagree. One has 0, another one has 1. And this distance satisfies triangle inequality, all the property of the distance between points on a plane. So mathematicians studied it many years before. It's metric space. And a good code is a code where all points are far from each other. Otherwise, you may end up with two closest elements, and you won't know which one. So, the minimal distance between two different elements is called Hamming weight of a code. A good code is a code with a large Hamming weight. Now, the best code in the world, it's amazing that it exists. One of the miracles of the world is Golay code. The length of the n tuple is 24. The dimension of the subspace is 12. And Hamming weight is 8. this Golay code is involved in a lot of mathematics, classification of finite simple groups, sphere packing, etc., etc. It's even involved in theoretical physics. And don't tell me that it doesn't have applications. When NASA sent satellite to Jupiter and Saturn, Golay code was used to decode signals. And in the United States, it is a standard for high-frequency radio. So this is the first example, coding theory. Another example. Public cryptography. In old times, if one general wanted to send a secret message to another general, they selected some page in a very thick book, War and Peace, and it was used to encode the message. It was very difficult to encode. It was equally difficult to decode it. But now, each time when you log in to your email account, you exchange secret message with your internet provider. When you use credit card or WeChat to pay, you exchange secret messages with your bank. Billions of people do it. Obviously, old methods did not work. And mathematicians came up with a new method that was entirely based on Galois fields. Suppose that, I will explain it. Suppose that Alice and Bob want to exchange some secret. And Catherine is a hacker. Don't read too much in names, it's just ABC. The following scheme is due to Diffie and Hellman. There are some other common schemes, all based on Galois fields. Let us choose a very large prime number p. I will explain why it has to be very large. Okay, so there are p reminders, 0, 1, 2, up to p minus 1. This is a finite field, as I explained before. Throw away 0. Then you are left with p minus 1 non-zero remainders. And now our operation is multiplication. In fact, in Professor Liu's talk, there were such examples. And this is a group. Galois even proved that this group is cyclic. So there exists some element G, more than one maybe, such that every element of this group is a power of that element that we call generator, G. Everybody knows these generators. Alice and Bob choose some secret numbers that they don't show to anybody, A and B. Then Alice takes the generator G and takes it to the power A and sends it to Bob. Bob got this G to the power A to the power of his secret number. So he knows G to the power AB. Bob does the same. He takes the generator G to the power of his secret number, G to the power AB, sends it to Alice. Alice takes it to the power of her secret number, so they both know G to the power AB. That is a secret that they share. What about evil Catherine? Evil Catherine knows P because, well, everybody knows P. She knows G because everybody knows G. She knows G to the power A because Alice sent it to Bob. She knows G to the power B because Bob sent it to Alice. But in order to know G to the power AB, she needs to know A and B. And we are coming to the problem of discrete logarithm. Take logarithms in the Galois field. If they were real numbers, she would just press a button and take logarithm, and that's it. But this is not a finite field. It is a finite field. It's not a field of real numbers. There are expectations or fears that when and if quantum computer is built, it may be more efficient in taking logarithms, but we have to wait when and if it is built. Okay, the last, well, I should say also that in the technology of blockchain and Bitcoin, the same methods are used. More often, instead of this group of non-zero remainders, they take some version of it, group relate encoded by elliptic curve, but ideally it's very close. In blockchain technology, sometimes you need authentication from your neighbors, and how do you do it? In the same way. All financial transactions in the world, all, are done on the basis of this scheme. Now I will explain how all smartphones work. iPhones and Huawei, they all use this method. A bit is 0 or 1. A byte is a sequence of 8 bits. So how many bytes do we have? 2 to the power 8, 256. Galois proved, among other things, he developed the whole theory of finite fields from scratch. So Galois proved that every finite field has order p to the power n, where p is a prime number. And for every p to the power n, there exists a unique finite field of that order. We could discuss what does unique mean in this sense, but let's not do it. So, I should tell you the story. In 2001, National Security Agency of the United States announced an open competition for the best encryption system. The winners were 2 Dutch mathematicians, Damen and Rijman. And so this method that I am explaining now, it's called either Advanced Encryption System or Rijndahl. First parts of their names. Okay. So the message is a 4x4 matrix over the Galois field of order 256. Well, to make it more difficult to read, we add some rows to another rows, add columns to another columns, we add key. But if it were only that, they wouldn't have won the competition. At some point, we do the so-called S-box. All elements in the matrix are inverted. It was A, now it is 1 divided by A. You may ask, what if it is 0? The inverse of 0 is 0. If you had tomatoes, you would throw them to me at this point, but I will explain why. It's a good question. How do you find inverse? Inverse is such an element that A times that inverse is equal to 1. How do you find it? Will you examine all elements? Too much. In fact, we find it via Lagrange theorem about finite groups. In a finite group of order n, the inverse of the element A is A to the power n minus 1. So, in fact, we are not talking about inverses. We are talking about powers. And power of 0 is 0. You need to do some 11 multiplications to find the inverse. Okay. In both Diffie-Hellman and Rijndahl, a very strong player can break it with supercomputers just by exhaustion. Like there was a terrorist act in San Bernardino, California. FBI wanted to read the iPhone of the terrorist. Apple refused to provide password. They broke it. But if you are an ordinary person, who would do it to you? If you are not an ordinary person. Every half a year, I read that somebody broke Rijndahl. I'm used to that. The recent was a week ago by South China Monitor. Okay, thank you very much.
Thank you so much, Professor. Please stay with us. Professor, may I invite you, could you please come to another side of the stage? The keynote speeches explore diverse topics in mathematics and physics. The discussion ranged from statistical physics and percolation theory to the evolution from natural numbers to infinity categories. Additionally, topics include 3D quantum field theories and line-length duality, concluding with insights on Evarista-Kalua's impact on communication technology. So now we're going to have a panel discussion. May I invite our moderator, Professor He Xuhua, and our panelists, Professor Ding Jian, Professor Liu Yifeng, Professor Hiraku NAKAJIMA, and also Professor ZELMANOV. So I may pass the stage to our moderator. Thank you.
So first, I would like to thank all the speakers for the wonderful talks. Now we actually move on to the panel discussion, and so the questions from the audience are very welcome. But to start with, maybe let me first read the topic. So and then we actually move on to see if the audience has questions. Actually, please raise your hand if you have. Well, first question I would like to ask you is that actually related to the mathematics and mathematicians and the careers. And so I know that actually there are many young students and also even the teenagers who want to be mathematicians. And so actually to ask you, what do you think are the important personality traits to be a good mathematician?
Okay. Well, first of all, I believe that there is such a thing as mathematical ability. You know, it's like musical ability. Just for some people it is easier than for other people. Second, stubbornness. Because when you work on a problem, you may work for many years, and in 99.999% of time, you don't achieve the result, and you have to do it again and again and again. Probably there are more traits.
Okay. I think that mathematics. I'm sure that this Japan and China has similar flavor. So this is based on the Asian culture. So we have the hard competition in entrance exam. So people may think that mathematics is used for competition, but it might be true for the educational level, but it's not so for the research level. I think that it's really important to emphasize that. So mathematics, research level mathematics is not competitive, and people do very different things, and this is just more cooperative effort of the community. So I believe that anybody who likes mathematics could be a mathematician.
Okay, so if I would like to mention one particular trait for mathematician, I think that would be patience. Okay, just as mentioned by Professor ZELMANOV. So most projects, especially in pure mathematics, they require a long period of working. Some may be several months. That already short, right? I mean, some long ones like Wiles proof from my last year, the whole length is like 8 years. Okay, so imagine that if one without patience could never finish a project lasting for those many years. So, but more precisely, so what does this patience play? Like, so first you have to stay there, like even after rounds of frustration, you still need to like keep the focus on the problem. And also there are many details. Lots of like things you need to work it out. lots of difficulties. One by one, you need to finish them. And all these things, no one else will tell you. Like, no professors will give you homework. Like, today, so which lemma, tomorrow, which one? No, you don't need to figure them out by yourself. And in some cases, like, unlike the problems you face in high school, the logic behind all this research is not linear. So it's not like one by one, then finally. Usually like this block, that block, then everything will patch together. The whole organization process and the whole solving process requires lots of patience. And that patience, well, maybe, I don't know if it can be developed, but I think it's a very important feature. If you think you have such patience, maybe it's a good idea to try to be a mathematician. Thank you.
First of all, I agree that you need certain mathematical ability to become a professional mathematician. There is some bar. Below that, I really don't think this is the track, at least for a career for someone. I think the second important thing is that you should enjoy it. If you don't find a pleasure in doing mathematics, there are really many other ways that can make a living in a much better and a much more efficient way. Then both Professor ZELMANOV and Liu talked about patience. You have to be persistent, spend years and years of efforts to trying to solve a puzzle. I agree with that, but I also would like to chip in the other side of the coin. You also need to have some sense on when to give up and switch to a new problem. Sometimes it's just maybe this problem is not right for you, or maybe it's not the right time to solve the problem, the right tools are not there yet. You can't just bump your head against the wall and hope something will happen. You know, you only have, your life is only once time. You don't have that many years that you can spend, you can waste in luxury and still secure a job. But the very cruel thing is, before we flip until the end of the book, we don't know whether your patience or persistence is for good or not for good. And this is a bit luck. I don't think anyone can tell you something definite. Okay, now it's the time that you should persist. Now it's the time you should give up. Nobody can tell you that. You have to build your own sense to make a choice when that kind of crossing road is present to you. I guess that's pretty much what I have to say, and I would like to pass it to the chair.
I'm curious. I mean, for that, actually, you just only depends on your own sense, or you actually also rely on the theory of probability.
Okay. Thank you very much. You actually reminded me of something that I was about to say, but I forgot, which is just answering the question, if you want to make a judgment on whether should it be basically coming from yourself or should be, you said luck or probability. But I think more importantly, you probably should talk a lot to other professional mathematicians to build a sense on what is the right thing to do. Usually the sort of right thing to do are connected to some other things. If what you're working on is purely isolated at this point, perhaps that's not the best thing to chase at the moment. Speaking of communication skills, you also have to develop certain skills to balance your life, to find pleasure outside of mathematics. Because as much as we hope that we enjoy doing math, frustrations is just there, very frequently. So for someone who wants to be a professional mathematician, try to develop some harmless hobby. Whatever it is, it doesn't have to be meaningful. As long as it can calm you down and bring some smile to your face. That's very important, I think, for mental health and for a long-term pursuit of mathematics. Thank you for your reminder.
Yeah, thank you very much. And I'd like to thank all the speakers actually for the valuable input how to be a good mathematician. And I would say that actually probably this is not only applies to the mathematics, but also, I mean, some that also actually apply actually to be, I mean, if you actually choose other career paths, I mean, to have a successful career or even have a happy life. And okay, I would like to say yes.
Hi, everyone. My name is Joseph. I'm in investment business. I am looking at opportunities in quantum computing, which is your area. So my question is, in your view, how likely is quantum computing, if likely, or you think it's unlikely? Because it's a game changer, so it's very important for investment, for crypto. So I'd like to hear your view about quantum computing. Thank you.
Quantum computing. The question is about quantum computing.
Game change? Which game? The whole game. Huh? Didn't understand the question.
Okay, I think he asks whether quantum computing can be real, and if so, how much longer should we wait, or something like that. How much longer you think quantum computing can actually be applied in reality? I think that's the question. Quantum computing, yes.
It's like cold fusion.
It's like what?
Like there is a thing as cold fusion.
Or is it real?
It may be, you know, both quantum computing and cold fusion can be, you know, it could be next year, or could be in 30 years, or never.
So it's not feasible. It's not really feasible yet, right?
No, at this point so far, no.
I appreciate it. Your honesty is very important. If you don't think it's feasible, then it's not feasible.
I think you should take the answer with caution. I don't believe any of us is a real expert in quantum computing. You will hear different things, different ways of talking from different people. Those who would like to push the area, and those different. Yeah, this is the time that I should echo what I said earlier. You should use your own judgment after talking to people. One single person said it's not impossible. It's not possible. Does not mean it's not possible. Another day you met another person who said, "Oh, it's very promising. In 5 years we're going to have it." It may not be the case either. So, yeah, I would just tell you I don't know.
I should actually probably say in the beginning of the panel discussion that actually all the discussion here will not be regarded as investment advice. Let's see if there are other questions from the general audience. I'd like over there. Please.
Hello, speakers. I'm very bad at mathematics. What makes me interested, because my son, 8 years old son, loves mathematics. So how he fall in love with maths, as simple as watching a video called Building Blocks at YouTube. Building Blocks is very visual-driven things, teaching you what is add, 加減乘除, so the basic 4 things. And then he suddenly he has the curiosity. And then last year I go to Cambridge to learn about sustainability and innovations. And I don't know where he knows that there's a bridge in Cambridge without any nails, but it's called mathematics bridge. So, and then he sent me, oh, you must go there because that bridge is called mathematics bridge. It doesn't come with a nail, but they hold together the bridge. So, so I feel really fascinated by how a simple video in YouTube, starting from visualizations, because kids, they are not good at language at start, but they are good at seeing, because they learn faster seeing. So, and then makes this how he fall in love with mathematics. And then when I'm in Cambridge, and then there's a guy echo to these questions about algorithm trading. So he is a graduate from Cambridge 10 years ago, and he's now doing the on Cambridge mathematics, and he's now doing the algorithm trading on investment. And the way he speaks is blah, 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 so fast. It's like his brainwave working this speed. So, so recently I just back from Dubai for a business trip. And you know, Dubai is a very unique space because
excuse me. So
the question is,
yeah.
I do believe in crypto because it's a digital world. But the problem is how you use these tools to change the world for a better humanity and a safer planet. I mean, in terms of environmental. Because in crypto world, everything is traced. Even in blockchain, everything is traced. So it's a force of energy. It's a force of energy, so everything is traced. So it's a force of energy and power on how people tracing or changing the economy or something in terms of community. So I think and even on the quantum computing, it should be the session in the morning. So I think there's a lot of interdiscipline sections to close the dots.
Yeah, excuse me, because our time is short. Would you please briefly raise your question?
Oh, so my question is how to make my 9-year-old son fall in love in this area of mathematics. Thank you. To solve the complicated problem of this planet and humanity in general. Thank you.
So let me try to repeat if I understand your question. So your question is that how to have this is a young kids to to like or fall in love with mathematics, right?
Okay, I think for most people who really like mathematics, they don't care about how useful is mathematics. So, well, mathematics, of course, help a lot in real world. But as mentioned already by many talks, there's no way to live mathematics in today's life. But mostly they are carried out by non-mathematicians. They are experts in other fields who use mathematicians. So I guess for kids, maybe it's way too early to think about. Maybe you can show some examples, like we know this. For example, all this general relativity or all this internet security, all heavily reliant on modern mathematics. But I guess that usually won't be the driving force, for someone to fall in love with mathematics, right? I still think, in most cases, math is really pure. I just found it interesting, challenging, and I feel very happy by solving some puzzles in math. That's how most people fell in love in math. And of course, there are struggles, there are pains, but that's part of the life, right? We all have that, but we still love our daily life. So that's, I guess, it will become natural at some point that somebody uses developments in mathematics to benefit our world or to influence our, no matter in which direction. At least there's a huge influence. That's for sure. That's what I want to say. Thank you.
Thank you.
One more question.
Yep. One more question.
I'm quite interested in Ding Jian's talk about the percolation. So I'm curious that I searched that there is a model called the random cluster model. And I have several questions. And one is that how can you make sure that is only one transition point on, between the unpercolated and percolated phase? And others are...
So since we are actually running out of time, maybe just only one question.
These are related. So if the random cluster model has a multiple dimension, how you can make sure before prove that the transition point is sharp? That's my question.
Thank you. So we have only 1 minute, and
I guess I will have to answer this one. For many models, when there is a monotonicity, then it's clear there should be only one transition. You transit from no percolation to there is a percolation. So when there is monotonicity, this is natural, and this actually happens in many models, including Bernoulli percolation, an easy model, and the Gaussian field I didn't have a chance to talk about. But there are also other cases when monotonicity is unknown. Then in this case, yeah, you could have very weird behavior potentially, but at least we have the faith that things should still behave nicely. For instance, when there is disorder, we don't really know things are monotone, but we still believe it would behave nicely. So answering your question, when we don't know what to show, when we don't know what is the actual truth, we have to have faith and try to prove it. It's like standing here still without doing anything is not as useful as making a guess of a direction and trying to jump to that. Because if you make a decision on that's the truth you want to pursue, you have at least a 50% chance of success. And if you choose the wrong direction, along the way, you probably will find, okay, something is probably incorrect in my intuitive picture, and you can switch back. I think this is how basically all science develops, not just mathematics. You need to make a decision on which direction to try. Okay, time is over. Sorry.
Yeah, I'm pretty sure that the audience actually has many more questions. Actually, feel free actually to ask the speakers afterwards. I mean, since we're actually running out of time, so our session has to end here. So let's join me actually to thank all the speakers for their valuable insights and inputs.
Thank you so much. Thank you. So we are now invite all the guests, please rise to have a photo together. Let's have a photo together. Please have a look to the center, please. Okay, maybe we can have one step to the left, please. One step to the left. Yes, perfect. Yeah, one step is enough. Thank you. So please have a look to the center. 1, 2, 3. 1, 2, 3. Okay, a few more to go. 1, 2, 3. Okay, thank you very much for the insights, for sharing. Thank you so much. Thank you.